Hello students, and welcome to Mr. Garofola's final exam review, Systems of Equations. Sorry I couldn't be with you guys today, but I recorded this video to help you through today's review topic, Systems of Linear Equations. So there are three situations that we learned this year can happen when we place two linear equations on the same coordinate grid, or graph two linear equations on the same coordinate grid, and that is that they could have one solution, and that is that they intersect one common point. They may have no solutions, which you see here, case 2, or they could have an infinite amount of solutions, which you see here, case 3. All right, so take a moment and pause the video here and try and see if you can remember what features would have to be true about the slopes and y-intercepts for case 2 and case 3 to occur. All right, pause the video now. Okay, so case 2 happens when the lines are parallel, right? You can see here that these lines are parallel. And this would mean that their slopes would have to be the same, but their y-intercepts would have to be different. If you contrast that to the infinitely many solutions in which all the intersection points are in common, you can see that this is actually two lines graphed overlapping, and this means that both their slopes and y-intercepts are the same. And that brings us back to case 1, in which the slopes are different, and that's what would cause the lines to at some point or another intersect. These happen to intersect at 2, 1. The 2, 1 is called the solution to the system, and the uniqueness of that point is that it would be the only point that makes both equations true at the same time. All right, so let's take a look at the ways we learn to solve these. So the first way we learn to solve a system is by graphing the system. So I want you to pause the video in a moment, and I want you to graph both of these equations on the grid here and see if you can find the solution. And if you found it, see if you can check whether it makes both equations true simultaneously. Okay, pause the video now. All right, so your graphs for the first equation is a y-intercept at -2 and a slope of 1/4. So we would move up 1 and to the right 4 for a slope of 1/4. And if we drew the graph connecting those points, it would look like this: y equals 1/4 x minus 2. The second graph, second equation, has a y-intercept of 3 and a slope here. It says -x, actually a 1 here, right? So the slope is -1 over 1. That's a vertical change of -1. That's down and then to the right 1. So down 1 to the right 1, down 1 to the right 1, and so on. Connect at those points. Y equals -x plus 3, and if we graph accurately, it's pretty clear that the solution is at the point 4, 1. All right, if we wanted to check our work on our graph, we would take 4, 1, and using 4 for x, -1 for y, we would substitute those values to see if it makes both equations true. So in the first equation, it would say -1 is equal to 1/4 of 4 minus 2. And 1/4 of 4 is 1, and 1 minus 2 is -1. So that would check. In the second equation, it would say -1 is equal to -4 plus 3. And -4 plus 3 is equal to -1. So we've just shown algebraically, by checking, by substitution, that the point 4, -1 does in fact make both of these true. and thus is the solution to the system. All right, so you're going to try this once again on the next problem. This time, one of the equations is in standard form. So you'll need to use some strategies we reviewed yesterday for that one. All right, pause the video now and try this problem out. All right, so let's see how we did here. On this first equation should be graphed as such. 1/2 x plus 3. Looks like this. And then 4x plus 2y, my preference here would be to graph by intercepts. So to find the y-intercept, I would let x equal 0 and find that the y-intercept would be 8. So 0, when x is 0, y is 8. So that would be this point up here. And then for the x-intercept, we let y equal 0. And we would find that x is equal to 4 when y is equal to 0. So that's the point 4, 0. This was the point 0, 8. It's this point here. And then you can draw the graph by connecting those 2 points. And this is y equals 1/2 x plus 3. 4x plus 2y equals 16. All right, so it looks like we have an intersection point here at 2, 4. So we believe the solution is 2, 4. Once again, I would encourage you to take those values and substitute them in to check your work. So pause the video now and make sure they check. All right, moving along, we then learned how to solve systems using algebraic methods. We learned something called the transitive property. And we applied that to the systems where both equations were in y equals mx plus b form. So take a moment now, pause the video once again, and see if you can apply that to solve this system of equations here. Okay, so the setup for this one should look like this. 7x minus 18 is equal to negative 3x plus 22. So for those that may have forgotten, the transitive property says if A equals B and B equals C, then A equals C. What does that mean? Well, basically, if y equals 7x minus 18 and negative 3x plus 22 equals y, since they're both equal to y, these expressions can be set equal to one another. And then we would use balance moves to solve. And we would get that x is equal to 4. Now, since we're looking for the solution to a system, this is only half of our answer. We also need a y coordinate. So we're going to take the x coordinate we believe is the solution and substitute it back into either equation in place of x. And then that should give us our y value out. So if we do the first one, y equals 7 times 4 minus 18, we get 28 minus 18, which is 10. So we believe it's 10. Let's see if it works in the other one as well. Negative 3 times 4 plus 22 would be negative 12 plus 22, which is also 10. So our y coordinate of our solution is, in fact, 10. These lines would intersect at 4, 10. All right, and then we finished up with the substitution method. And this would be useful when one equation is in standard form, like the first one here, and the second one is in slope-intercept form. And I want you to pause the video now and see if you can recall how we would use algebraic methods to solve this type of system. All right, so this method is called substitution because we're taking the expression that is set equal to y and we are substituting it for y in the other equation. So since we know y is equal to 2x plus 1, we're replacing y with 2x plus 1 in the first equation. So it would say 2x plus 4 times, not y, but 2x plus 1 is equal to 16. Notice our equation now only has x's in it. So when we go to solve our system, we are going to end up with a solution for x first. So we'll be using a distributive property here first, and then we may need some balance moves. We actually have some terms we can combine here on the left side. And find that x is equal to 1.2. Alright, so if we substitute 1.2 back into one of our original equations, now in this case, probably easier to use this equation here to find our y value. So we have 2 times 1.2, which would be 2.4, plus 1, which would be 3.4. So the y value, 3.4, so we're saying the solution here is 1.2, comma 3.4. Alright guys, so there's a brief summary of the Systems of Equations unit. There's still some more work to do in this packet on the last page. Try your best on it, and I will see you in class soon.